Okay, let's prove this kind of property. First of all, let's see the associative law. Here's proof. First of all, let's say there is the matrix C with the column vector C times C1 through the CP, something like that. And by definition of the matrix multiplication, the matrix B times C is going to be B vector C1 through the B vector CP, something like that, right? Then what is the A times BC? Something like that. So it should be something like this. Then it will be A BC1 through the A BCP, right? Right. Then by definition of the A times B, so this will be the A B times C1 through the A B times CP, right? So it means that it will be the AB times the matrix matrix C. Okay, so this is the left side here. This is the right hand side. So this is the proof of the associative law. Okay, law. Okay, so similar to this one, you can prove these kinds of things, right? So please try to derive the proof of the remaining things by yourself. Okay, this is also very intuitive, or you can check the proof in the textbook or the website. So please try to drive this. Okay, in this class, let's move on. Okay, here's one more rule. If the AB is equal to the B times A, then we say that A and B is A and B commute with each other. So this is a very special case. The A, B is equal to B times A. Okay. Here's the example. Okay, let's say A is the n by n, P is the n by P. Okay. First of all, what is the A times B? Size of the A times B? It should be n by P, right? From here to here. What about BA? If the m is equal to P, it will be the n by n. But generally, if the m is not equal to P, we can't compute the P times A. So generally, we can say that A times P is not equal to P times A, right? So, but fortunately, this A times B is equal to B times A. So in this case, we call this case as a commute with each other. Okay. So in other words, in generally, the A times B is not equal to B times A. And another thing is that the cancellation laws do not hold for the matrix multiplication. What does it mean? If A times B is equal to the A times C, then it is not true. It is not true in general that B times C. What does it mean? Okay, let's say 3. Let's think about in the algebra domain. Okay, 3 times 2 is equal to 3 times 2. Then we can say that this B, let's say this is A, then in this case we can say that P is C, right? But in the matrix domain, P C A C, then generally B is not equal to C. There's a case when B is equal to C, but generally it's not true. So please be careful. Finally, the product A times B is the zero matrix. Then we cannot conclude the either A is equal to 0 or B is equal to 0. It means that even though matrix is not 0, matrix P is not 0, then AB might be 0. Even though this case, right? So please keep in mind this is very frequent mistake when think about the matrix multiplication. Okay, please be careful. Okay, there is one more concept, the powers of the matrix. Okay, let's say we have a matrix A with a n by n, the square matrix, right? Then and K is the positive integer, something like the 1, 2, 3, something like that. Then AK, A superscript K denote the product of the K copies of A. So it means that AK is equal to A times A times A times A times A times. So in this case, the product of the K copies. Okay. So in this case, this is called the powers of the matrix. Okay. So here is an interesting rule. If A is the non-zero and X is in the Rn space, then AK times X is the result of the left multiplying X by A repeatedly 8 times. So what does it mean? So it means that we can multiply A on the left hand side of the vector X and multiply A again repeatedly k times. So in this case, A k x or the powers of a matrix, right? What about k is equal 0? In this case, the A0 times x, then we define the A0 times x as x itself. A0 times x is x itself. So what does it mean? In this case, this is the identity matrix, right? So in case of the identity matrix, we can say that identity matrix times vector x is vector x itself. Okay, so this is the property of the power of the matrix. Okay. There's one more concept, the transpose of the matrix. Okay. M by M matrix A, the transpose of the A is the N by N. So let's say this is M by N. The transpose A should be N by M. Then this is represented by A transpose, and whose columns are formed from the corresponding rows of A. So this column from the rows of the A. So this row will place down here, right? Something like this. So this is the definition of the A transpose A. So for example, if we have a matrix A 1, 2, 3, 4, 5, 6, then in this case A transpose will be the what? 1, 2, 3, 4, 5, 6. Okay. So this is the concept of the transpose of the matrix. Then here is here is the theorem for the transpose of the matrix. Let's say the matrix A, P denote the matrix whose size appropriate for the following sum and product. Transpose A of transpose is the A itself, matrix A itself. Okay, the first thing. The second thing, A plus B transpose is equal to A transpose plus P transpose. And AB transpose is equal to B transpose times A transpose. And for any scalar R, RA transpose is the R times A transpose. Okay, so this is the theorem. Okay, in today's lecture there are many theorems, so please summarize each theorem by yourself. Okay, this is very important. Okay. Okay, so before finishing, I would say you can also prove this transpose, right? So this is also very intuitive, so you can do this one by yourself. Okay. Okay, let's move on to the next section. This section is related to the inverse of the matrix. So, okay, let's start the lecture 5.2. Okay, what is the inverse? What is the inverse of the matrix or matrix inverses? Before starting, let's think about the inverse in algebra. Here are some examples. There's the integer 5, and what make this equation is true? What makes 1 over 5, right? Or 5 inverse, something like this, right? Or we can compute, we can multiply 5 superscript -1 on the left side, also something like this. So in this case, this is called the inverse of the scalar value 5, right? So this is inverse in the algebra space. Then same things happen in the matrix domain. Let's say we have a matrix A, and there is an identity matrix, and what make these two equations are true? What is that? This is the inverse of the matrix. Okay, so let's see what it is. Okay, here are some definition. An n by n matrix A, the square matrix, right, is said to be invertible. If there is the n by n matrix C such that C times, okay, let's use this color. C times A is equal to the identity matrix IN, and A times C is equal to the identity matrix, and in this case, C is the inverse of the matrix A. Okay, so this is the definition of the inverse. Then this C is uniquely determined by matrix A. Okay, so in this case, we can denote this C as a inverse of matrix A. Okay, so this is the definition of the matrix inverses. Okay, so how can we prove? Because if there is another vector, another matrix B, and B were another inverse of the A, then we can write down P is equal to P times identity matrix, and is equal to P times AC from here, right? Then we can say that PA times C and is equal to IN times C, because by definition this is IN, right? Then finally it will be the C. Okay, so from this equation we can say that V is equal to C. So it means that there is a unique inverse of the matrix A. Okay, so this unique inverse is denoted as A inverse like this, right? So we can represent A inverse times A is equal to the identity matrix, and A times A inverse is also identity matrix. Okay, so this is the definition of the inverse of the matrix A. Okay, here is another theorem. Let's say A is the 2 by 2 matrix with the entry A, B, C, D. Okay, then A is invertible. If A is invertible, we can represent the inverse of A as a 1 of AB minus BC with a BDA minus B negative C, right? I guess all of you already knew about this matrix invert, right? In case of the 2 by 2 case. So actually this I won't prove this theorem, but in the determinant section we will discuss what is the general formulation of this inverse. So before that, just keep in mind this is the some examples of the matrix inverse. Okay, in this case, if the AD minus BC is 0 here, it doesn't exist, right? So in this case, we can say that A is not invertible. If AD minus BC is not equal to 0, then A is the invertible. Okay, this is very easy. So as I discussed, AD minus BC is called the determinant of A. So we can write the determinant A as something like this, right? So it means that this theorem say 2 by 2 matrix A is invertible if the determinant A is not equal to 0. Okay, so this is a very simple case of the determinant, but when matrix 3 by 3, 4 by 4, or n by n, the concept of determinant will be the very difficult. So we will discuss further in the following lecture. But here, let's just keep in mind in 2 by 2 case. Okay. Okay. Here are one more theorem. Let's say matrix A is invertible n by m matrix. Then for each vector B in the Rn space, then Ax times B. Actually, we are interested in the Ax times B until this lecture, right? So Ax times B. Here is the Ax equals B. Okay. So the equation Ax equals B, it has the unique solution as a x is equal to A inverse B. Okay, so to prove of this theorem, we have to answer the two questions. First one is the existence, right? Because the solution has to be existence as x equals A inverse times B, right? Then another question was the uniqueness, because they say there is a unique solution, right? First of all, to prove the existence, the solution exists because if A inverse P is substitute for the X, for example, something like this, then it will be something like that. Then this is A times A inverse B. Then by definition, this is the identity matrix, right? Then this will be the P itself, right? So what does it mean? The A minus B, inverse of A times B is the solution of the AX equals B, right? Right? This is a proof of the existence. What about the uniqueness? To prove that solution is unique, show that if another vector u is any solution, then u must be the A inverse B, right? Then let's say if AU is equal to B, then we can multiply both sides as a inverse of A, then we can get A inverse here with A, B, something like that. Then this is the identity matrix by definition. Then we will finally get the vector U is going to be A inverse A times B here. So in other words, the U is equal to A inverse of A times B. So we can say that this is equal to vector X, and this is the unique solution. Okay, so from this proof, we can conclude if matrix A is an invertible, then for each vector B, the equation Ax equals B has a unique solution, as X is equal to inverse A times B. Okay, so this is the theorem. Okay, there are one more theorem, right? There's so many theorems. So first of all, if the matrix A is an invertible matrix, then A inverse of A is also invertible. Then inverse of matrix A of the inverse is going to be matrix A itself. Okay, this is the first theorem. The second theorem, if the arbitrary two matrices A, B are n by n invertible matrices, then the inverse of the A times B is the product of the inverse of A and inverse of B in reverse order. Then it can be represented something like this. So inverse of A times B is the product of the inverse of A and inverse of B in reverse order. Okay, so this is another theorem. There's one more theorem. If matrix A is invertible matrix, then the inverse of the A transpose is the transpose of the A inverse. It means that inverse of the A transpose is the transpose of the inverse of matrix A. Okay, this is the theorem related to the matrix inverses. Okay, let's see the proof. First of all, to prove this one, find another matrix C such that A inverse C is equal to identity matrix and C times A inverse is identity matrix. Okay, then these equations are satisfied with A in place of C, something like this, right? By definition, right? by definition of the inverse matrix inverse, right? Therefore, A inverse is the invertible, right? Then A is the each inverse. So in this case, this term has the inverse as a Okay, so this is a proof of this equation. Okay, the two proof of the property B here. Compute the AB times P minus P inverse A inverse is going to be AB P inverse A inverse, right? Something like this, right? Then this is the identity matrix here. So finally, it will be the A times A inverse, right? So it will be the identity matrix. Similarly, this term can be derived as a identity matrix I, right? So it means that this is the inverse of this one. This term is the inverse of this one, right? So this is the proof of this term, right? And finally, A inverse transpose A transpose will be the A minus A times A inverse transpose. Why? Because we already know the AB transpose as a P transpose A transpose, right? So from here, right? So we can get this one. Then this is in identity matrix. So something like that. Then the similarly A transpose A inverse transpose is also I. So we can say that AT is invertible. AT is invertible. So each inverse will be the A inverse transpose. So A transpose here invertible and has a inverse as this term, right? So we can represent A transpose inverse is A inverse and transpose. Okay, so this is a proof of the those property. Okay, so there's one more concept. It is called the elementary matrix. Okay, so elementary matrix. Elementary matrix is one that is obtained by performing a single elementary row operation on an identity matrix. What is the elementary row operation? What was that? Why we need this? Because to solve the linear system, we have to row reduce the matrix, right? So to row reduce, we need some elementary row operation, right? There was three kinds of those row operations, right? What was that? Please check what is it? What was that, right? So anyway, there was three kinds of the row operation. So the elementary matrix is the matrix form of this elementary row operation. Okay, let's see the example. Here is the three matrix. Actually, these are examples of the elementary matrix. E1 looks like this. There are L1 values on the diagonal with -4 here, right? Another matrix E2 is something like this. Interestingly, it has the these two values are exchanges from the identity matrix, right? Let's think about identity matrix, something like that. What is the elementary E3? Here is the 1, 1, but there is the another integer values on the diagonal, something like that, right? So in this case, there is a matrix A here, okay? So in this case, let's compute the A1 times E1 times A, E2 times A, and E3 times A, and describe how this product can be obtained by elementary row operation on A. Okay, let's see. First of all, how can I compute the A1 times A? E1 times A. What is the E1? What is the E1? 1, 1, 1, 0, 0, 0, 0, negative 4, 0, right? And A was A, B, C, D, E, F, G, H, I, right? Then, what is this one? This row times this column, right? So it is the A. What about this? What about this? This row times this column, right? What about this? This row times this column, right? So in this case, this is the 1, 0, 0, 0. So this first row first row of the matrix A itself. Okay. What about this one? This term is the second row by first column, right? This is the second row by second column. This is the third row by third column, right? So it's also second row of the matrix A itself. What about this? What about let's use the different color here. Okay, what about this? This is this row times this column, right? So it means that negative 4 times A plus 0 times T plus 1 times G. So it means that this is a G negative 4A here. Something like that, something like that. So what does it mean? This is similar to the addition of the negative 4 times row 1. Negative 4 times row 1. Row 1 here, right? To row 3 itself, right? So it means that there was the replacement operation in the row operation, elementary row operation, right? So this is the case of the replacement operation. So it was something like this R3 minus 4 R1, something like that. But rather than using this term, we can represent this as a matrix multiplication E1 times A, something like that. This is much convenient, right? So this is examples of the elementary operation, replacement operation. What about this one? What was the E2? E2 was 0, 1, 0, 0, 1, 1, 0, 0, 1. with A, B, C, D, E, F, G, H, I, something like that. So this value is this one times this one. So this is the D. This value is the this one times this one. So this is E. So F, right? So we can compute this one. So what is that? This is the interexchange between this one and this one, right? So this is the interchange operation. Interchange operation, something like R1 with R2, right? So in other words, without using this notation, from now on we can use the E2 times A to compute the interchange of the row 1 and row 2 of matrix A. Okay? What is the last one? What was the E3 here? So 1 1 0 0 0 0 0 0 what? 5 with the matrix A, B, C, D, E, F, G, H, I, something like that. So this one is this vector times this one. So 5G, 5H, 5I. So what is that? This is a multiplication of the row 3 by 5. Something like row 3 will be the 5 row 3. So this is the scalar multiplication operation. This is the E3 times A, something like that, right? So to summarize, the three kinds of the elementary law operation: replacement, interchange, scalar multiplication can be represented by E1, E2, or E3, something like that. So it means that by using this elementary matrix, we can row reduce the arbitrary matrix A in a matrix space. Okay, so this is the elementary matrix. Okay, so elementary row operation is performed on the m by n matrix A. The resulting matrix can be represented EA, where the m by n matrix E is created by performing same row operation IM. Okay, so there is what does it mean? What does it mean? Okay, let's see the detail on here. And then the elementary matrix E is immutable. This is a very important concept because it means that the inverse of the elementary matrix will satisfy this one and this one. Okay, this is the property of the elementary matrix. Let's see this one. Let's see this theorem before understanding this one. Okay, on m by n matrix A, m by n matrix is immutable if and only if the matrix A is row equivalent to the I and the identity matrix, and in this case, any sequence of the elementary row operation that reduce the A to IN also transform IN to the inverse of A3, inverse of the matrix A. What does it mean? Okay, let's say we have an arbitrary matrix A here. And by using some kinds of the row row operation, we can derive the IN from the matrix A. It means that there are several kinds of the row operation, right? Something like the interchange replacement, or the linear scaling, something like that, right? So, okay, let's say this is the transformation. Let's say the T, okay, the set of the row operation, right? Then, if there is a some transformation T, then by using this same transformation, we can derive the inverse of the matrix A from the identity matrix, something like that, with the same transformation T. Okay, so this is the meaning of this theorem. Okay, so let's prove what it is. First of all, let's suppose the matrix A is invertible. Then, since the equation AX equals B, X equals B has a solution for each B, each B, then A has a pivot position in every row. Since to understand this concept, you have to see the lecture 4. There was theorem related to the pivot position and inverse. Okay, please check this. Then because the matrix A is a square as a n by n, right? Then it means that there is a n pivot position, right, on the diagonal, something like this on the diagonal, right? That implies that the reduced echelon form of the matrix A is a IN matrix. IN, the inverse identity matrix. So, okay, we have a matrix A. There are some kinds of the row operation here. Then make some vector matrix B in R, E, F form, reduced echelon form, something like this. But the matrix A is a pivot position in every row, right? So pivot position, something like this, right? Then what is the property of the REF? The pivot position has a value 1 here, something like this, right? So, and this is 0, right? So what is that? What is that? This is the identity matrix, right? Right? So in other words, from the arbitrary matrix A, we can derive the row reduced echelon form. Then it is the identity matrix itself. Okay. Okay. Then from A matrix, and we derive the identity matrix. Then let's suppose conversely some arbitrary matrix A is converted to the identity matrix. Then each steps of the row reduction of the matrix A correspondent to the left multiplication by elementary matrix. So it means that starting from the arbitrary matrix A, some arbitrary elementary matrix E1, A, E2, something like this, blah 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 blah, EP times this one. Okay, so this matrix will be the any kinds of the row reduction row operations, like the interchange, replacement, or scaling things. Then by definition it should be in identity matrix IN. Then to summarize, set of this row operation, the set of the elementary matrix times A should be identity matrix, right? Since the product of the invertible matrix is also invertible because each matrix are invertible, right? Then it leads to inverse of the EP times E1 times EP through the E1 A. This term, and this term, okay? Because there exists the inverse of the EP through the E1, right? Then this should be what? This should be what? Identity matrix, right? Then finally we can get the A is equal to this one, right? A is equal to this one, right? Then A is invertible by definition. If invertible, as it is the inverse of the invertible matrix, so inverse of A will be the, from here, inverse of A will be the this one inverse this one, and by property of the inverse, this one will be the EP times E1, right? So then A inverse is the EP through the IN, right? So it says that A inverse of the A results from the applying the E1 through the EP successfully to IN, right? So this is the same sequence in let's say yeah, this is the equation 1. This is the same sequence in 1 here that reduce A to IN, okay? So this is the proof, okay? So the conclusion, to conclude, if the matrix A is invertible, if and only if A is the row equivalent to IN, right? So in this case, this matrix A is invertible, and any sequence of elementary row operation that reduce the A to IN will also transform identity matrix IN to the inverse of A matrix A. Okay, this is the theorem of the elementary matrix. Okay, so what does it mean? So what is the relationship to this theorem and this property? If the elementary row operation is performed on the m by m matrix on A, and the resulting matrix will be the EA, where m by m matrix is created by performing same operation on IN. Then, okay, there is the elementary operation E, that it will be the E, right? Then this elementary operation E? We can find this one from the identity matrix to the what? Same operation, because this is the EI, so this will be the E, right? So in other words, to find the elementary E, we can perform the same operation on the matrix A and I simultaneously. Then we can find the this elementary matrix E. Okay. So what does that mean? We can use this proof to derive the inverse of the matrix A. Let's see the example. Wait. Okay. So yeah. So yeah, here is the algorithm for the finding A inverse. Yeah. Almost done. So why we learned this chapter? we are interested in finding the solution of the A is equal to B, right? To find the solution, in the previous section, we used the low reduction algorithm to reduce this sum arbitrary matrix A into the REF form, right? Or A, then we saw find the solution from REF form, something like that, right? But if we can find the inverse of the matrix A, then by multiplying inverse of matrix A, something like that, we can directly find the inverse B. So this will be the solution, something like this. So by using the sum matrix technique that we learn in this chapter, we can find a more efficient way to find the solution. X is going to be A inverse B. Okay? So yeah, here is the definition. So the low reduce. So how can I find the inverse of matrix A? First of all, let's low reduce the augmented matrix AI. Okay. And if A is low equivalent to the I, then AI is the low equivalent to the IA inverse, right? So it means that AI, then if we use some kind of the row operation to get the row equivalent to the identity here, then this row operation also makes some inverse of the matrix here. So this one, from this one to this one, will make this one to this one, okay, with the same row operation. Okay, so what does it mean? By making this matrix A as an identity matrix, we can naturally find the inverse of matrix A here. Okay, this is a very important property. Okay, wait up. Give me 10 seconds. Where is that? Okay, let's move on. Okay, let's see the example. Here is the problem. Let's find the inverse of the matrix A. Let's find the inverse of matrix A when matrix A is equal to something like this. Okay, how? First of all, let's write the AI something like this, and then row reduce this matrix as a identity. Then in this case, we can naturally get the inverse of matrix A here. Okay, so this is the inverse of the matrix that we want to get. Okay, so okay, here is the matrix. This is the matrix A here, right? This is identity matrix, right? Then, okay, let's row reduce. How can you do that? First of all, we have to exchange the first row and second row, right? Right. Then this one. So it will be the first row in the previous matrix. This will be the second row in the previous matrix, right? Okay, we have a 1, 1 here. What do you want to do next? We have to remove this one. How? By using this first row. So we can get this one from this row minus 4 times this row, right? Something like that. I will skip the whole of the procedure, so please do in yourself, okay? Then we get this one. Then what do you want to do next? We have to remove this part, right? How? By using this row. So we get this one, right? Then we have to make this one as a 1, right? Then we multiply the 1/2 on this row. So here, yeah. Then finally we have to remove this one by using this row, right? So we can use this one and this one. We can make this one. So finally, this is the identity matrix, right? So AI, the input here, we make the identity matrix here. Then finally, what is that? What is that? This is the inverse of matrix A here. This is the solution that we want to get, okay? So because the arbitrary matrix A is low reduced to the identity matrix, so then A is invertible, then it means that the inverse of the matrix A is going to be this one, okay? How can I check? Just multiply original matrix A with this inverse of matrix A. So this is the original matrix A. So this is the inverse of matrix A. What is that? This one times this one. So what is that? Here are some problem, right? It's not a here's, yeah. So it makes some 1, right? What about this? This one times this one. It will be the what? 0, right? What about this? This one times this one. Okay, so it will be the 1. So finally, this whole matrix will be the identity matrix. Okay. So this is the algorithm for finding the inverse of matrix A. Okay. So yeah, I will skip this one. This is the concept. This is a way to interpret the matrix inversion, but it's not a very good. It's not closely related to the inverse. So I think that this part is really important. So please try to follow the whole procedure by yourself. Okay. So this is the end of the matrix inverse chapter.